everyone, I'm Nurul Hazrina binti Nordin from UMPSA STEM Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
Hi, welcome everyone to this course on FPGA-based digital system design. This course is designed to introduce you to the world of digital hardware design using Field Programmable Gate Arrays or FPGAs. As the industry moves towards hardware acceleration and embedded systems, FPGA programming has become a crucial skill. This course will guide you through the process of designing, simulating, and implementing digital circuits using hardware description language and industry-standard FPGA tools. This is a Micro-credential series on digital system design. This program is a comprehensive journey through the modern silicon design flow. We will bridge the gap between abstract logic and physical hardware using industry-standard tools and the Altera DE10 Lite FPGA board. Let's break down the 3 modules that will define your expertise in this subject. Module 1, Fundamental of IC and HDL Design, focuses on the what and the how of hardware description. By the end of this module, you will be able to design, simulate, and verify both combinatorial and sequential circuits at the RTL level. We begin by exploring the digital design abstraction hierarchy, moving from behavioral models down to physical implementation. In this module, you will learn the following topics. Chapters 1 and 2, you will gain a historical perspective on programmable logic from PLA to FPGA and dive into Verilog syntax and data types. Chapter 3 and 4 will cover structural, data flow, and behavioral modeling styles while teaching you the critical art of writing test benches and interpreting timing diagram in Model Sim. The associated labs to these chapters are Lab number 1, Blinking LEDs on the DE10 Lite, your first step into the hardware, and Lab number 2, Mastering Switch Inputs and Debouncing Logic. Moving to Module 2, the RTL Design and Synthesis, shifts the focus to transformation and performance. It's one thing to write the code, it's another to ensure that the code translates efficiently into hardware. You will learn to analyze digital system performance using functional synthesis and validation techniques to ensure your design are hardware ready. In this module, we'll cover Chapter 5 and 6, RTL representations of encoders, decoders, and complex finite state machine using milli and more architectures. Chapter 7 and 8, you will learn advanced verification strategies, waveform debugging, and the logic synthesis flow, specifically how Quartus maps your RTL to a gate level netlist. Here, we'll do practical labs exercise on Lab number 3, designing and analyzing a 4-bit adder on the FPGA, and Lab number 4, implementing a complex FSM for a satellite communication link simulation. Module 3 focuses on timing analysis and design optimization. This is where we archive professional grade reliability through timing closure and hardware deployment. You will end your journey with a class project, integrating all your RTL modules into a complete, optimized digital system that meets industry standard for quality and testability. These final chapters include Chapter 9 and 10, Mastering Static Timing Analysis. We'll tackle setup and hold times, critical path and optimization techniques like pipelining and retiming. Chapters 11 and 12, you will learn to navigate Quartus compilation reports, manage resource utilization, and use the logic analyzers for on-chip debugging. The associated labs are Lab number 5, Implementing Pipelining to Boost System Frequency, and Lab number 6, Timing Analysis and Critical Path Exploration to ensure your design never fails in the field. From the first line of Verilog to the final timing close bit stream on your DE10 Lite board, this micro-credential equips you with the full stack skills required for modern digital design. In this class, we utilize Verilog as our primary language managed within the Intel Quartus Prime environment. To ensure your logic is flawless before reaching hardware, we integrate Model Sim. Unlike basic in-house simulators, Model Sim provides industry-grade functional verification and deep waveform analysis, allowing you to catch complex bugs early in the design cycle. Your digital design experience comes to life on the Altera DE10 Lite FPGA, where you will learn digital design concepts and implemented it onto FPGA, making use of its onboard components such as LEDs, switches, and 7-segment displays. To extend your immersive experience in this class, we have integrated Lilacs 4 Little Explorer 4 platform. The Lilacs 4 is a homegrown extension board developed by UMPSA STEM Lab, specifically designed to augment the DE10 Lite. Lilacs 4 features an array of onboard sensors, giving you the unique opportunity to design digital systems that interact with the real hardware. You won't just be processing bits, you'll be interfacing with environmental data, mastering sensors integration, and seeing how digital logic responds to physical stimuli. As you navigate these tools, you will learn to operate across the 3 critical levels of design abstraction. Behavioral level, where we define what the system does using high-level algorithmic description. RTL, register transfer level, the sweet spot of digital design, where we define how data flows between registers and the combinatorial logic that transforms it. And physical level, the final frontier, where your design is mapped to actual logic elements, routing wires and pins on the FPGA. From your first line of Verilog to the final timing closed bit stream on the DE10 Lite and Lilacs 4, this program equips you with the full stack skills required for modern engineering. You aren't just coding, you are architecting silicon. As you navigate these tools, you will learn to operate across the 3 critical levels of design abstraction. The behavioral level, where we define what the system does using high-level algorithmic descriptions. The RTL, register transfer level, the sweet spot of digital design, where we define how data flows between registers and the combinatorial logic that transform it. And physical level, the final frontier, where your design is mapped to actual logic elements, routing wires and pins on the FPGA. From your first line on Verilog to the final timing closed bit stream on the DE10 Lite and Lilacs 4, this program equips you with the full stack skills required for modern engineering. I look forward to seeing your design comes to life, from a simple blinking LED to a high-performance sensor-driven system.